Hi, this is Maria, and tonight we're going to talk about chemical and physical changes, and then using equations to describe them. So really, the goals of this video are pretty simple, just discussing some equation vocabulary, and then learning more about physical and chemical properties, and then also physical and chemical changes, which you've discussed those in class. Alright, so let's just start with some equation vocabulary. Why do we even need equations? Why do we need these chemical equations? Well, when we're talking about a chemical equation, we're really just describing what's happening at a molecular level. There's some important terminology related to this. So there's coefficients and there's subscripts. And we've talked about subscripts before because you've used them in ionic naming. But coefficients, they're just the big numbers in front, and they're always used to indicate how many of each element compound are present. There's something that end up possibly being changed. We'll talk about this more when we get to balancing equations themselves. But it's really how many you would need in order for the reaction to proceed in the way that it's laid out in the equation itself. And then subscripts, remember, those are those tiny little numbers, and they really just tell you how many of each atom are present in a compound. So, for example, in water, we know there's 2 hydrogens for every 1 oxygen. Both coefficients and subscripts, if there's no number in front, so like over here with the hydrogen gas, if there's no number in front, we just assume that it's a 1. Same sort of thing with the subscripts. If there's no subscript written, it just means that there's a 1. This is also a great equation for reviewing the different states of matter, which you've probably heard a little bit about at this point, but just something to be aware of. So there's solid, that's what the S stands for, liquid, and gas. Those are all pretty obvious. But for the other physical state that's pretty important that we'll be using a significant amount, it's aqueous. So really what that just means is something that's dissolved in water. Do you remember that if it's an ionic compound, that means that this is actually dissociated, right? That means I have a hydroxide floating around, and I have a sodium ion floating around. All right. Do also remember that we have reactants on this side of the arrow, and then we have products on this side of the arrow. It's really, 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 really important to include a few different things in every chemical equation. Make sure that if it's information that you know, the physical states of each compound should be present. So solid, liquid, gas, or aqueous should be by every single compound listed. And it should be correctly balanced. In the beginning, you're going to get the equations either balanced, or we're just not going to care about the balance. Eventually, it's going to have to be balanced, and you are going to be required to do that. And it's really, really important to be aware that you are going to need to have an arrow, not an equal sign. It has to be an arrow. It can be something, it's got to be something that looks somewhat like this. Turns out there's different arrows in chemistry. We'll talk a little more about a different type of arrow that you could be using, but it turns out it's really important to use an arrow that looks somewhat like the one that you see here. All right. So, physical properties. So, a physical property is just a property that could be measured or observed without changing the identity of the substance. So that's something like density. You can measure density pretty easily. You just take the mass, you take the volume, awesome, you figured out the density. Melting and boiling points. You haven't changed the identity if you're figuring out the melting or boiling point. You might be changing something else, like the appearance. If you're doing melting, you're going from solid to a liquid, boiling, liquid to a gas. And remember, that's just the temperature at which you're melting at, or boiling at. And then color. That's also something else that you can observe without changing the identity. So physical changes, you've discussed that in class, but it's really just where the appearance of a substance changes, but the identity does not. Okay, so water going from a liquid to a gas. You can see that the identity of it doesn't change. The only thing that's really changing is that we're putting energy into the system in the form of heat, and that's just causing the liquid water molecules to get farther away from each other because now I have a gas. And so a great example of this could also be carbon dioxide. Water's not the only thing we can talk about here. So solid carbon dioxide, if it was going from solid to liquid, which you've really only seen it going from solid to gas, but interestingly to think about, this would be a pretty good way to represent it in terms of a particle level diagram, which you've practiced a little bit now. Remember, solid, really, really nicely organized. There's a little bit of movement, which is important to just be aware of. You don't have to necessarily show these wiggle lines. Liquid, I would expect to see the different particles farther apart from each other. And then gas, much, much farther apart from each other. You don't necessarily have to show movement in particle level diagrams. I liked this one because I thought it was a good example of a good way to show movement, but that is very much up to you. Physical changes in equations, so remember, when we're talking about a physical change, that means that maybe the appearance has changed, but not the identity. I still have carbon dioxide at the end of this process. It's just now in a gas as compared to in the beginning of this process, it's a solid. Interesting. All right, so chemical changes and chemical properties. Chemical properties really just describe how substances will react to different elements or different conditions. There's a lot of examples out there. So your reaction to water, whether you're flammable or not, your reaction to acids, those are all great examples of chemical properties. And chemical changes are really ones where a substance will go an identity change on the molecular level. Really what we're saying, a chemical reaction has actually occurred. So this can be often identified by observing any of the following. Temperature change, production of gas, which usually if you're looking for it in class, it'll be bubbles. Color change. Precipitate, so some sort of solid, usually like a powdery thing, sort of like what you got over here. Production of light is also a possibility. Usually that'll go hand in hand with some sort of temperature change where there's a production of heat and production of light, but not always. So just a thing to be aware of. So this is actually a reaction that I'm going to have you look at again at the end of the video. This is the formation of solid lead iodide. So just something to look forward to. When we're talking about this with equations, again, we want to always make sure we include our physical states as long as they're known. And if you're trying to do a particle level diagram, now you can kind of see here, I have the same number of white spheres on both sides. 1, 2, 3, 4. 1, 2, 3, 4. But over here it was attached to this black sphere, which is representing the carbon in this methane molecule itself. And then over here, it's actually attached to an oxygen. So that's pretty different. And so you'll notice that it's the same number of each of these different types of each of these different colored spheres, but they're just rearranged. That's all it is. So when we're talking about chemical changes in equations, it's really just this idea of, oh, if I'm drawing my particle level diagram, I just want to show that, oh, this is now with this, and this is now with this. They did it in this particular way by just using different colored spheres, but you might not have that available to you, or you might want to do squares and triangles, and that's fine. Just make sure that when you're drawing that particle level diagram, you make it very clear of like what's your reactants, what's your products. So if I were doing a particle level diagram for this, I would suggest saying, okay, well, if I have a methane molecule, it looks something like this. If I have an oxygen molecule, it looks something like this. And then my product side, I'm going to want to make sure that I have these all mixed together in some sort of form as well, where again, you just have your spheres, different colors or different shapes, whatever's easiest. All right, so I know this is a longer one. You do need to try this problem. So here's a chemical equation, and it's got lead 2 nitrate in an aqueous form reacting with sodium iodide in its aqueous form, and then it forms a solid lead iodide, lead 2 iodide, and sodium nitrate, which is an aqueous. So simple enough, physical or chemical change. What sort of sign of a reaction would you actually see? So think about those 5 things that I listed earlier. And I know this is going back to what you learned about in class today, but if you're thinking about the end products, would you see a heterogeneous or a homogeneous mixture? And then draw those particle level diagrams for this reaction. So take a look at the tips that I have below here. Other than that, do your best. That's all we're looking for, and we'll definitely go over it in class the next time that you see your teacher. All right, have a good night, and we'll see you soon.